This is Dr. Mughal here. Welcome to another tutorial. In this one we are going to create an up counter which is going to count starting from 0 to 9, and once it does that it's going to flash an LED. Let's look at the functional block diagram. We basically going to have two modules. One would be for the 7-segment display. The other one is going to be the counter, in which we're gonna have different sub modules. The counter, the 4-bit counter, and the clock to slow down to at a frequency of 1 Hertz. Let's start with the project. Let's create a new project here. Now that the project has been created, we are now going to create a new source file, which are we going to name as display. 7-segment. We are now going to add our inputs and outputs, and if you look at the block diagram, we basically have 4 inputs which we are going to name as digit, and 7 outputs which are basically the 7 segments of the LCD screen that we have on the board. Here is the skeleton source file for the one that we just created. As I write the code, I'm going to comment each line in the code so you can better understand. So these are the 4-bit value to be displayed as 0 to 9, and these are the 7 segments on the 7-segment display. Also, please notice we are going to declare this variable 7-segment as register, but just for the sake of your understanding, I'm not going to add or declare that variable as a register as of now, and see if this would work or not. We are going to create a set of constraints for the 7 segments, basically using the command parameter to declare the binary values for each digit that could be displayed on the LED 7-segment. Remember here, the leftmost bit is actually the segment A, and the rightmost bit is for the segment on the display. We'll do this coding for the rest of the other combinations starting from 0 and all the way to 9. We are now going to use the case keyword or case statement in order to define the values for the 7 segments. And again, like I mentioned before, we have to declare this 7 segment as a register, which we haven't done yet, but I was just wanted to show you that if we don't do that and when we compile our code, it's going to return an error. And because this counter goes from 0 to 9, so we will basically have 9 cases. By default, we are going to choose the 7th segment to display 0. So this is done for the display part. Let's see if we have any errors or not. We have 4 critical warnings, so let's try to troubleshoot those. Looks like I am missing a semicolon on line number 47. And also missing a semicolon on line number 54. Let's save it and run synthesis on this file. See, I was telling you, it is going to return us an error if we don't declare the 7th segment as register, because we want to store the values for each segment on the display. There you go, awesome. We're not going to worry about the implementation part, but let's now move on to creating a new source file, which we are going to name as counter. It is also going to serve as a top module for this project. Let's look at your schematic again, the functional block diagram. You basically have 2 inputs. One is going to the reset, the other one is going to the clock, which is 100 megahertz. We need to remember, we need to cut it down to 1 hertz. We also have 2 outputs. One would be the 6th segment and 4 enablers for the 7th segment in order to enable them. So let's declare them as an array. We are also going to have an LED as an output. Once every 10 seconds have occurred, the LED is going to flash. Again, I'm going to do the same thing. I'm going to comment out each line in the code so you can better understand. The clock FPGA is basically the 100 megahertz FPGA clock. This is the reset button. If pressed, it's going to start the counter back again from 0. These are the 7 segments and the 4 enablers for the segments on the LED 7 segment display. Also LED being used as a flasher when 10 seconds have occurred. I'm going to use the parameter in variable name max count, because we have to cut down the frequency from 100 megahertz to 1 hertz. Therefore, we are going to use a counter which is going to count 100 million times. So we're looking at 0 to 99,999,999. So the simplest way I could write it down is 100 million minus 1. We also have a counter enabled as a wire, which is going to enable the counter every 1 second. And also we are going to declare this counter underscore 10M as a register, because we are recounting up to that value. So we need a higher number. So 0 to 27 bits would let us have that big number. And then of course the counter to count from 0 to 9. In this project, we are only going to use one of the displays, so let's use the rightmost board, and because it's an active low, so we have to make sure the rightmost bit is set to 0 and the other ones being off. Let's now first instantiate the display module that we just created. Remember here, the counter underscore 10 signal is going to be our input, and it changes every 1 second, so it will start from 0 and go to 9. And segment signal is connected to the 7th segment display. So input, which is counter underscore 10, comma output, which is segment. And I'm using a variable name SEG for that, so I need to change it to SEG. Let's now create a slow clock. This is something that we have done in the past, but we would actually create a different source file and then call the function. Here we are going to integrate everything into one source file. So creating a counter to divide the 100 megahertz frequency clock to 1 hertz. We always start with saying always at positive edge clock FPGA, which is the 100 megahertz clock, and the positive edge reset. If the reset button is pressed, you want your counter to be set to 0. Else, if the counter reaches the maximum value, which is 100 million in our case, we would want the system to restart every 50 million clock cycles, because one complete cycle contains the on and off. So if you divide 100 million by 2, you have 50 million cycles. And if the clock is not set to 0, then increase the counter by 1. Now let's move on to creating a counter to count from 0 to 9 at a frequency of 1 hertz. So again, we start off by using the always at command. When the positive edge of the clock arrives, if the reset button is pressed, the counter is set to 0. Else, if the counter enable is high, which is for the clock, every 1 second the clock arrives, and the counter is equals to 9, this is when it needs to restart, or in other words, reset. So the count goes to 0 here, and if that's not the case, then we would want the count to go up by 1. Now finally, we would flash an LED every 10 seconds, because that would mean 1 cycle of the counter has occurred. So we're just gonna say assign LED equals to, and when the counter reaches a value of 9. Let's end the module. Go ahead and save your file and see if there are any errors or not. There are a few errors, looks like. Line number 49. I believe I'm missing 1 0 on line number 49. It should be 100 megahertz. I really encourage you, as you make those changes, keep on saving and synthesizing your file. I think I have the same issue on line number 51 as well. I'm missing 1 0 here as well. And on line number 57 as well. Let's go ahead and save it and compile it. Fail again. Looks like there's one more error I have on line number 57. I believe this should be counter, so I was missing ER. One more thing I forgot to add here was the counter enable. Remember, we would want the counter to go up by 1 every 1 second. So creating a signal that is active every 100,000, every 100 million clocks. So we say assign counter underscore 100M equals to 0. This is when it resets. This is when it has reached its maximum value, which was 100 million. I think the code is pretty much done now. I'm going to create a constraint file now. What all we need is a clock first up. We also before we move forward, we need to make sure the name of the clock matches exactly with the way we have written in the code. We need 7 segments, also LED actually, which flashes every 10 seconds. the 7 segment and the 4 enabler. You're not going to use the decimal point, so let's just put hash next to it. You also need one push button for the reset, and that's pretty much it. We will go ahead and save this file and run the implementation now. Make sure you change the name to reset. Hopefully there are no errors. Awesome, it went through. We are now going to program and debug. So let's start off with creating a bitstream file. Now that we have a bitstream file created, we are going to open the target. Make sure your Basys 3 board is connected to the computer. Program the device. And enjoy the implementation of your circuit diagram on your Basys 3 board. Thank you for watching. It was a very simple tutorial, but there was a lot of stuff to learn. I hope you enjoyed this one and keep on watching. If you haven't already, please subscribe to the channel, and I shall see you guys in another video. Thank you for watching. Bye.